Okay, well, thank you very much for the introduction and for inviting me to give a presentation in this seminar. I think kudos to you and Knut for keeping this going for the last 4+ years. It was a very welcome venue for many of us during the pandemic, and I'm excited to see that it continues to thrive. So today I'm going to talk about an inverse problem in EIT. Um, Basically, it's the problem of determining a small conductivity anomaly in EIT with minimal measurement. I will explain a couple things later. One of the key things that I want to mention is what I mean by measurement. This is joint work with Carsten Chen, who is a graduate student here, and Asil Titi, who is a postdoc here. So in traditional EIT, I'm sure that you're all very familiar. The idea is that you want to determine the conductivity in the interior of a body from boundary measurements. And a measurement in classical EIT consists of applying a boundary current, which represented by by F here, and then you measure the voltage on the boundary. And a measurement means that you have chosen a current distribution, and then you measure the boundary values of the boundary potential. In the classical EIT, you have the entire map, which means that you have every possible pairs of possible F and the measured data. And so what you determine here, you can actually determine this, is that you can find sigma, which is the conductivity distribution, from the totality of the Dirichlet to Neumann map. There was work in 2019 by Alberti and Santacesaria, in which they proposed that if sigma, the conductivity, can be represented with a finite number of unknowns, then finitely many pairs of F and boundary values, the U at the boundary, suffice to determine sigma. So they're still thinking about this abstractly as a theoretical problem. It was made more real by Haraj, also in 2019, where he shows that if you have finitely many electrodes, the conductivity which can be represented with a finite number of unknowns can be determined from this finite number of measurements on these electrodes. So our motivation for this work comes from a paper by Isakov and Titi in 2022 in the context of inverse gravimetry problem. So in this problem, as you recall, you have you measure du dn. I'm sorry, you have an anomaly, gravity anomaly, and you have in their problem, they want to measure a minimal amount of information in order to find the shape that describes this gravity anomaly. Traditionally, how you would solve this, the traditional way that this problem has been posed is that you usually have gravity measurement over a surface or over a curve or some measurement set, which is not a point or a few points. So the departure that they took in addressing this problem is just to see how many measurements do you really need if you can measure at a point. So at these points, they measure the gradient of the gravitational field. And so the way that they approach this is that they assume that the anomaly is inside a ball of radius rho. And for rho relatively small relative to the size of the body, forward map between the shape and the measurement can be simplified. And it is straightforward to show that an elliptical anomaly can be located and characterized. So motivated by this, we were asking if we can do something similar for electrical impedance. So what what we decided to do was to set the problem up in the following way. This is sort of an engineering solution that sort of mimics the kind of measurement that Isakov and Titi propose in their work. So in here, I'm going to try to see if I can get my laser pointer to work. Let's see, where's the laser pointer? Maybe not. Okay, here we go. So I'll just do this with the full screen. So I'm going to look at the linearized inverse problem, this where the conductivity is a constant background plus a small perturbation supported in set D. We're going to assume that both gamma and D are small to make the calculation simple. So we'll be looking at a linearized problem where you have the voltage potential has a background potential plus a perturbation. And so the equations for the background is just Laplace's equation. And we're going to assume that the for the boundary condition current for the background solution, we're going to apply a dipole. Of course, a dipole can be an approximation of something with two electrodes, which is pictured here. So I have current coming in here and going out here. And so we're creating a dipole field or an approximation of a dipole field in a physical space here, which is going to be a unit circle just for simplicity. The unknown is this green blob. And so the field that's created by this pair of dipoles is very easy to write out. And it depends on the location of the dipole, which is the angle phi. Okay. So now we need to choose what we mean by a measurement. So you created this dipole field. And what I'm going to do is I'm going to go back to the classical Calderon identity and write down the identity. And in this very simple case, because of the fact that the conductivity is constant in the green blob, the only thing that shows up here is the product of the gradient of the harmonic test function with the background. And it's integrated over the support of the blob. And the data which you collect would show up here. And that's going to be, again, integrated over the surface with the test function V. If we choose V to be also equal to the U0, which is the background field, then the measurements, roughly speaking, is the tangential derivative of U1 at this location, at radius 1 and angle phi. And again, it can be approximated by measuring the voltage at the pair of nearby electrodes. So in my imagined system, I'm sending current here and taking it out here, at the same time measuring the voltage drop between them. So basically, I'm using an ammeter or an ammeter on the surface to measure the conductivity that I would the impedance that I would get at those electrode points. So if I accept this as sort of the model for the forward problem, then you have this this equation, the measured tangential derivative at the boundary approximated by this voltage drop across two very nearby electrodes is equal to the integral of the gradient of the background field squared integrated over the unknown region D. So as you can already see now, if I can move this pair of electrodes around, meaning I move my voltmeter around the boundary of the object and measure the voltage drop across the electrodes, then I should, in principle, be able to determine what this shape is. um, for this problem. Okay, so I just wanted to show what this gradient of phi, gradient of u0 squared looks like for a given angle phi. The angle is right here. So the background potential is very classical. It looks like this. This is at the equipotentials. The lines are drawn out here in this picture. And the probe, in a sense, the field that is created, that's probing the unknown, is shown on the right as this picture here. It's quite large near where the electrode locations are and gets very small far away. So you would expect it to be very sensitive if you have a conductivity anomaly nearby, but not so sensitive, it's far away. So I can now pose the inverse problem. We have the forward map, which happens to be just basically an unknown phi, an unknown d that we want to determine, and an angle where the electrode pairs are located, integrated over the domain d. In the function gradient of u0 squared is integrated over the domain d. And the inverse problem is to find d, given that I have made these measurements at a few angle phi. So if the anomaly is a small ellipse, then with axis A1 and A2, and location at B1 and B2, and an orientation that's given by Xi, then we only have 5 unknowns. So in principle, we should be able to determine the unknowns characterizing the ellipse with 5 measurements. Maybe I should pause for a second and see if anybody has a question. Please raise your hand so we can see who has a question. Okay, no questions, so I'll just go on. So it's a pretty straightforward inverse problem. Discrete number of unknowns, and we just have to generate a discrete number of equations. So let's look at the forward map in a little bit more detail. If the ellipse is small, the forward map reduces to this very nice formula with the parameters of the ellipse being B1, B2, the location, and A1, A2 being the axis, and C being the orientation. You can actually write down a formula that is approximately equal to the area of the ellipse, multiply this set of terms. The first term depends only on the center of the ellipse and the angle at which you are locating the electrodes. The second term is a little bit interesting also, but it also splits the terms into terms that depend on the ellipse, geometry, and the location of the ellipse and the orientation. So if you think of the ellipse as being represented by the vectors T1 and T2, then you have the following quadratic form. T1 times the matrix K times T1 is, then you add the next term, which is T2 transpose K times T2 as the additional term. So you can see that there's a split between the geometry of the ellipse and the location and where you measure. The K itself is pretty straightforward. The big K is just the gradient of the background field squared. And then K, the script K is basically the Hessian of that function. And they both depend on the dipole angle and also the ellipse center. This can be derived using polarization tensor as described in the very early paper of Sadio Fenya, Moscow, and Vogelius. The formula comes out exactly the same. So I will now focus on locating and sizing the ellipse first. So if you think about this problem, if you just want to know the center of the ellipse and its size, locating the center is like a process of triangulating, right? If you have three measurements, you should be able to triangulate and locate where the center of that green blob is. And in fact, that's the case. There's some really nice geometry going on here that I think it's worth spending a couple of minutes to think about. So here in this picture, I have the unit circle where the domain and that I'm probing, and I placed three locations where electrodes are where measurements are being taken. So they're denoted by 1, 2, and 3. Okay, so a couple of interesting facts. There are two circles associated with each pair of measurements. If you think of the third point as being sort of the reference point, if you draw a line between the electrode 1 and electrode 3, the center of the circle, this circle C1, is actually on this line right here. The center of the circle C2 is on the line connecting 2 and 3. So and the radius themselves depend on the ratios of the measurements that you would get over here, and over here. So let's call R1 G3 divided by G1, which is the measurement obtained at 3 divided by the measurement obtained at 1, raised to the power, I think it's power 1/2, sorry. I don't know why there's a 3 there. And then the R2 is G3 divided by G2 to the power 1/2 as well. Then the radii of these circles are determined by these numbers. Okay, the radii of the circle C1 is determined by R1. The radii of the radius of the circle C2 is determined by R2. The two circles, if the data is consistent, the two circles would intersect. And where they intersect, which is in this case is this point here, is the center of the ellipse. So it is like a triangulation, but in this kind of a weird geometry that is dictated by the background field, basically. So you can easily locate the center, and once you have the center, you can easily back out the area. So we can actually show that this is true as long as the data is consistent. The ellipse center and its area are determined from 3 dipole measurements as long as the phase are distinct. So take any 3 measurement angles, you should be able to find the location of the center and the area of the ellipse. As for stability, we can actually explicitly compute the Jacobian of the mapping between data. In this case, I'm actually looking at the mapping between the ratios that I described here, R1 and R2, and the location of the circle, of the ellipse. And there's a bound that we can calculate, estimate, of the inverse, the size of the inverse of the Jacobian. And it has 2 terms. One term, this one, is small if the dipoles are close to the anomaly. And the next term becomes large if the angles are too close to each other. So this term tells you that you should put the dipoles close to the anomaly, but this term tells you that you should also spread out the dipoles as much as you can. So there's a trade-off here, and you can ask yourself a question, where should you put the measurements? So this leads us to the next question that we were very curious about, which was the optimal placement of these electrodes. So we went to the subject to look for this area of research, and it is a very well-developed area in statistics. It's used quite a bit in linear estimation problems, and there's a Bayesian framework that's also appropriate for nonlinear problems. In this case, we need to use a nonlinear framework because the relationship between the ellipse parameters and the data is nonlinear. But let's look at the linear version first. For linear problems, optimal experiment design is equivalent to finding the best design matrix when you're doing, when you're doing a regression task. So consider a simple linear regression where you have only two unknowns, theta 1 and theta 2. And you're going to choose the place where you're going to measure, and you're also going to read out where you're going to read out the output. So you want, in a typical regression problem, you would choose a bunch of x where you measure and find out what the output is, the y's. And from these pairs, you would like to be able to estimate theta 1 and theta 2, a very classical problem in linear regression. So how do we pick the xi's? So if you look at the equation, you have basically an overdetermined system if you have more than two measurements, measurement xi. And so you have this overdetermined system. The least square solution is basically obtained by writing down this formula. This gives you an estimation of the parameter theta. So if you know that the reading that you're getting for the y is going to be noisy, with the noise being normally distributed with mean 0, the covariance of the estimate of theta is sigma squared times x transpose x inverse. This is called the information matrix. So the statisticians have come up with different ways of describing optimality in measurement. One is called A-optimal, where you try to minimize the trace of x transpose x. And then there's the D-optimal, which is minimizing the determinant of x transpose x inverse. And then there's the E-optimal, which is minimizing the maximum eigenvalue of x. So basically, if you think of the level lines of the covariance in these two-dimensional problems as ellipses, what you're trying to do is trying to make this ellipse as small as possible. That gives you the highest certainty. Okay, so I want to give an example and also give some intuition about what's going on here. So in the case of linear regression, which is the task at hand here, if you only do two measurements, and let's say that x is limited to be in the interval between 0 and 1, then the best choices are you choose one at 0 and the other point at 1, or you choose one at 1 and the other point at 0. There are two possible best choices. So you get the best estimate of the slope and the intersection using this choices. Now, what if you are allowed to make more measurements? What would you do? So when I started looking at this problem, I thought, well, maybe you should take a bunch of points in the middle. Well, no, it turns out that the best choices for the next few numbers of measurements are again to choose 0 or 1. So you always choose 0 or 1. The reason being that the more samples you take at 0, the smaller the variance of the y that you will be measuring. Likewise, or the likewise you will have the same property at the end. So you will do best by choosing by repeating your measurement over and over so that you reduce the error in the mean anyway. So that's the intuition that this is giving us for this particular problem. So now, what if you have a nonlinear problem? If you have a nonlinear problem, the situation is more complicated. So there's a Bayesian approach that's described back in '95 by Chaloner and Verdinelli, and about 10 years ago in a paper by Juan and Marzouk. So if you using the same notation, if you think of the forward map as f, in which the parameters are theta here, and the experiment is indexed by d or described by d. Suppose we have a prior on theta, then we want to seek d that gives the maximum information gain from the prior to the posterior if you actually execute a measurement. So that can be described in the following way. So there's a proxy for information gain in Bayesian statistics, and that's the Kullback-Leibler divergence, KL divergence. It measures, roughly speaking, the distance between a prior and a posterior. So for our problem, in this case, we're still thinking about the problem of finding the area of the ellipse and the two variables that places the center of the ellipse. The inverse problem is G I at this measurement phi equals to this forward map plus some noise epsilon. We can write out the KL divergence if for a given experiment. So the KL divergence in this case is, so you have a posterior and a prior. And this is given by this formula, which takes the posterior, the logarithm of the ratio between the posterior and the prior, and then integrate it against all possible parameters. And now, in the optimal design, we haven't done an experiment. So we have to look at all possible experiments. So to do that, you have to integrate over possible experiments, and this is what you get. This is the utility function that you need to consider for finding the optimal location phi. Okay, so in this case, you have this utility function that you want to maximize, and it's the expected KL divergence over all possible measurements. This is a very computationally very hefty thing to have to consider because of there's no closed form formula for most problems, and for that reason, the most likely way you can do this is by simulation. So this is a way that we can choose the three places where we measure to get the shape, to get the location of the ellipse and the size of the ellipse. So we went ahead and tried this experiment. And I'm going to take a couple of minutes to go through this experiment. So I have a ground truth. This is the ground truth values. The area is 0.01. Remember that it has to be pretty small. And the location is given by B1 and B2 here. This is the ground truth, but I assume that I know a prior. The prior is that the size of the ellipse is 0.01 with standard deviation of 0.05 squared. And then B1 and B2 are at, I have an estimate of the the mean location is 0.4 and 0.3, and the variance or the standard deviation is 0.2 squared for each of those location parameters. So now I go through the experiment design. In this case, we actually try to compare the best experiment with the worst. The worst happens to be getting yourself as far away from the unknown as possible over here, and bunching the electrodes, the measurement points, to be close to each other. The best measurement obtained through this optimization of the expected KL divergence puts us somewhere approximately like this, where the location of this electrode, the middle electrode, is roughly closest to where we think the prior tells us the object is. And then it places two electrodes at equidistance from the left and right of that center one. And you can tell the difference between the effectiveness of the good measurement and the bad measurement. In the good measurement case, the parameters A, B1, and B2 are very well estimated from the data. You have exactly the same A, a little bit off for this, and a little bit off for B2. On top of that, because we are doing this using a Bayesian approach, we actually have confidence bounds. The confidence bounds are very small. It's between 0.0105 and 0.0110. Okay, so this thing, it says that the area is between the lower bound and this upper bound. And then B1 and B2 also have a very tight lower and upper bound, confidence bound. When you do the worst experiment with placing the electrodes as far away as possible from the object and bunching them together, your estimate of the location and the area are way off, and your confidence bound are also quite large. You can see it, it's almost an order of magnitude bigger than what we have here. So it pays in this case to do something more than just doing the, just taking 3 measurements somewhere. I think this is a place where I would like to maybe rethink about how we always approach inverse problem. We have been very much a passive consumer of measurement or of data in inverse problem. Somebody measures data for an inverse problem, and we say, okay, fine, I'll work with what you give me. In this context, in this new context that I'm proposing, we actually have a dialogue with the people who are doing the measurement. We ask them first, how much do you know about what you're trying to determine? That means we have to have some prior information. And from that prior information, we use some kind of optimality approach to tell them what measurement they should measure for us, so that we can do the inverse problem as well as we can. So this is, in a way, a shift in the business model of doing inverse problems. I would like to think that we should be actively involved in the measurement process as well, and we should come up with tools. This is just one of them, of telling them what are the best ways to measure. One other aspect that I think is worth thinking about is are there other proxies for information gain? So another possibility is that at the guess value, where you are, if you're doing it iteratively, you get an estimate of the area and the location. The next thing you do is you find from the guess value, you find dipole locations that gives you the best condition number for the Jacobian of the forward map. And this can be set up as a sequential design problem, a greedy sequential design. This idea was already explored by my work with Michael back in the 1990s when we were trying to do the crack determination problem. We actually set up electrodes at a finite number of places on the boundary of the object we're probing, and we iteratively estimate the location and then choose in the next set of experiments in which to measure to get a better estimate. And at the end of the day, what you hope to gain is that you get a very good estimate of the parameters, but also the most stable estimate in the sense that the Jacobian is as well conditioned as possible, meaning that it will be less sensitive to noise in the measurement. This actually brings up an interesting point, which is worth thinking about, and it has been thought about by Marzouk and his collaborators, which is if you have a finite measurement budget, if you say to yourself that I can only make n measurements, which n measurements should you do? One possibility is to do an all at once. You just think of it as a static problem. But maybe more interesting is to think about it as a dynamic programming problem, where you have a sequence of measurements, and in each step, you have a reward that you maximize so that at termination, you have exhausted all the possible rewards you can get out of the system. So that's one way to think about this problem. When you want to try to find all the 5 parameters, you can come up with the following strategy, which we implemented in our paper. You choose 3 location to estimate. You choose 3 measurements first to locate the elliptical anomaly and its area, and then you use this information that you've gotten as initial guess in the Newton's method and try to get all the 5 parameters. But what we found was that the numerical experiments we found pointed that the major and minor axis and the orientation of the ellipse are very poorly determined from data. A small amount of noise would already wipe out your ability to find them. So what is robustly found can be easily found from this setup are the area and the location of the ellipse. I gave this talk maybe a week ago at Drexel, and Jingni was there, and she asked me the question. She asked me the question over dinner if you can do even less measurements. On the train back from Philadelphia, I started thinking about it, and I think the answer is yes. You can imagine a measurement like the following, where you place 3 electrodes, 1, 2, 3. You assign current I1, I2, and I3 to these 3 electrodes, but the sum of this current has to be 0. And then you measure voltage at those 3 electrodes. And again, there has to be a constraint on the sum of the voltages. If we perform 2 such experiments, we will get 4 independent equations. So that's more than enough to determine the size and of the elliptical anomaly. And I think this can be done. So we're starting to look into this. But I think another problem that would be nice to be settled, and I know there are a lot of analysts in the audience here, is to actually try to solve the nonlinear problem. Try to see if you can, without going through the linearization, can you actually determine the shape and size of the ellipse from 3 measurements. Okay, so I'm going to end with a discussion. So I describe an EIT problem with simple shapes. The measurements that I imagine dipole measurements, which can be approximated with a pair of electrodes. And this is a different kind of measurement than what we are used to thinking about in the EIT, which is that you prescribe an F, a current distribution, and then you measure the voltage on the boundary as one measurement. In this case, we really mean one point measurement, which is the resistance from a pair of electrodes that you place on the boundary of the object that you're probing. And we are very interested in the question of minimal number of measurement. If your unknown has a few parameters, can you determine this with as few? What is the least number of measurements you need to determine that unknown? We show an example, which is the size to determine this location and the size of an anomaly. We can uniquely determine this from 3 dipole measurements. We can establish stability, which also reveal that there are some better choices of, there are some choices of electrode locations that are better than others. And then we also looked into the question of optimal design, borrowing ideas from optimal experiment design in statistics. We also discovered that there's sensitivity to determining the other parameters of the ellipse, and that also is something that we can't see how to overcome. I mentioned the dynamic programming approach, which could be interesting to do, and the something that that maybe there are other proxies for information gain in terms of measurements, and we have explored the KL divergence and possibly the condition number of the Jacobian of the forward map. But there may be others that could be equally effective and maybe easier to compute. The one difficulty with the KL divergence is that you have to use some sort of sampling, and that's very computationally intensive. The more dimensions you have, the more parameters you have, the higher the dimension of the space that you have to sample, and the more computationally intensive that becomes. So with that, I will end the presentation, and I will be happy to answer any questions that you might have. Thank you.
Thank you very much, Fadil, for the very interesting talks. Thank you very much. Are there any questions or comments, please?
I think Matthias, please.
Please.
Unmute and I thought Matthias was first. Matthias, did you have a question? You're muted, unfortunately. Or maybe not. Okay, Jandian, go ahead.
Okay, so I have 2 questions. So first question is that if you have 2 small ellipses, they are pretty much near each other, and you use your formulation, what you are going to end up with? One ellipse, which is summarize all the information, or 2 ellipses?
Yeah, unfortunately, that's probably what's going to happen. We haven't really looked at multiple objects, and if they're close to each other. I guess, yeah, I don't know how to answer that question. That's a good one, and we haven't really looked into it. What is your second question, Janliang?
The second question that you see if we can start with the initial gas a circle, then that you can in that setting power you can easily determine like area and the location. Use that as some kind of prior information to further determine other things. Is that possible?
Yeah, that's what we did in the case where we tried to find the orientation and the major and minor ellipse, major and minor axis of the ellipse. We use the area and the location as initial guess, extract initial guess from that, and then we use the Newton's method to determine the other parameters. But we found that this determination is unstable because the data is just not very sensitive to the shape of the ellipse.
I see. Okay, thanks. Yeah.
Thanks for your question. Bill.
Yeah, beautiful talk. Lovely idea to use a minimal number of measurements. My question is there anything to be gained from a non-minimal number? Perhaps especially in the dynamic programming context. Suppose you can spin some more measurements and chase your anomaly around the circle. Is there any sense of whether there's more to be gained in terms of statistical stability?
I think there is. I mean, if you look at the linear, I guess the illustrative example is the linear regression problem with two unknowns. If you just do two experiments, you know that you have to measure at the far ends of your interval x, 0 or 1. If you have more measure, you've given a more budget to do more measurement, you reduce the error in the places where you have already measured. So I think even in the dynamic programming case, I think it's probably possible to see that the after a few steps, the next step is also to measure the previous step, because I think there's information gain, because every time you measure in the same space, you reduce the noise by repeating the same experiment.
Yes.
So I think there's something to that. The one problem that we've been struggling with is trying to see if you have all-in-one measurement, you choose n electrodes, do it once, or you do it greedily, start with, let's say, 2 or 3, and then keep going, adding one at a time until you reach n. And then the dynamic programming approach, we don't know how to rank order which one's going to be better. It would be nice to have a sort of a global theorem that says, if you have the choice, you should do dynamic programming, or you should do the greedy algorithm, because the dynamic programming is not going to give you that much of a gain. It would be nice to have that kind of a gap of how much information gain there is from the 3 different approaches.
Thanks.
Thanks, Bill. Anybody else?
Yeah, any other questions, please?
Can I have one more question?
Sure.
Okay. So, do you have some idea on how this kind of thing will be carried out in 3-dimensional setting?
Yeah, that's a good question. So in the work of TT and Isakov, they did look at 2 and 3 dimensions. There, the problem is a little bit easier because the mapping is just basically from potential theory, and they were able to come up with formulas that were very similar to what you would get in 2D in 3D, but the number of measurements, the amount of information you get from just point measurements of gravitational measurement is actually very similar in 2 and 3D. In electrical impedance, I think the situation is a little bit more complicated, and I don't see an easy way to do that, because one of the things that we exploited heavily in our work is how easy it is to write the background solution. I don't know of a background solution that I can write down that involves very simple measurements on the boundary.
I see. Okay, thanks. Yeah. Very nice.
Thanks.
Thank you very much. Are there any other questions or comments, please? Please feel free to unmute yourself. Any other questions or comments, please? Okay, if not, thank you very much, Fadil, for the very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you.
Thank you.